All right. The next talk is by a colleague of mine, Margus Veanes. And in a strange twist of fate, I happen to be a co-author on this paper. So if somebody wants to double check my timing, I'm trying to be very accurate. You're welcome to do so, but I am going to hold him to the same set of constraints as the other authors. Take it away.
So thank you for the introduction. And so yeah, so this is work together with Thomas Ball, the same Thomas Ball who's also the session chair. So I have this unique opportunity. If I get difficult questions, I can delegate them to the session chair. Anyway, so, and Gabriel Ebner, who's a collaborator here, and then Ekaterina Zhuchko from Tallinn Technical University, who's been working on this with us. So let me start by giving you a little bit of history about regularity, omega-regularity, and derivatives. Now, derivatives, this word has appeared at least twice in both talks. So let me give you a little bit of background. I go rather quickly because it can take a long time here. So from regular expressions introduced by Kleene, roughly 10 years or so, a decade later, Zhuchko introduced this notion of derivatives that actually applies to the regular expressions in extended manner. So you have also intersection and complement there. This was actually inspired, so this work inspired Thomson's algorithm. Although he didn't support the other operators, just the standard regular expressions, but he explicitly sort of says that in his paper from '68. It took a while, there's a bunch of work on derivatives, but not in the sense of matching or regular expression work, until partial derivatives were then introduced by Antimirov and then used a lot also in other contexts in '95. And then it was then in 2009 that Owens and other people then realized that a bunch of the theory that Zhuchko initially introduced has somehow been forgotten. And in particular, that you can actually very efficiently deal with complement and intersection in the context of regular expressions and get it to work fast. So this work was actually then, we investigated it further in the implementation of Z3 regular expression with Caleb Stanford and Nikolai Björner, and integrated this idea, and we generalized these derivatives to a symbolic setting where conditions can be arbitrary modular theories conditions. And this work later then also affected the implementation of a new non-vectoring engine in .NET, and it was recently also formalized in Lean. Now, if we look at the parallel track of Buchi Automata, we have omega-regularity, then the core work of relating the Buchi Automata to regular languages by McNaughton, and then the introduction of LTL, or linear temporal logic, in '77 by Pnueli, and then the study of LTL and tableau methods by Wolper, but also noting that the LTL is not expressive enough for certain very common properties. And then at the same time, alternation elimination algorithm or roughly at that time, from alternating Buchi Automata to non-deterministic. And then Pnueli also wrote a seminal paper where noting that omega-regularity is really something that is needed in general purpose temporal reasoning. And but also Emerson proved some correctness or precise theoretical result in that line of work. And then finally, I'll stop here by saying that then one of the sort of really foundational insights by Vardi was this way of taking a formula and incrementally transforming it into an automaton that we call Vardi derivatives here. And I will make precise what this notion means in a few slides from now. So the motivation for our work here is looking at omega-regular properties and using them in a context where we realize that LTL in itself is not sufficient. In practice, you need regular expressions to describe omega-regular properties, as pointed out. Often you also need modular theories to work with a large alphabet. And this is something we studied with Loris a while back. And there is a summary paper that I point to here. Then modular theories have played a crucial role in many contexts, like temporal stream logic, the symbolic execution work that we just heard about, and then also in the next talk, which is on reactive synthesis, again, it's LTL extended with yet more powerful techniques, but also modular theories. So there are many applications, numerous applications to both linear temporal logic and regular expressions and automata algorithms, but typically not for the full class of ERE. Essentially, what I mean by ERE is extended regular expressions with complement and intersection. And we realized that symbolic derivatives that I will introduce, at least through examples here, provide a really powerful framework, a unifying framework, both going from regexes in Z3 up to actually really fast matching algorithms. So I'm really encourage you to attend the talk on RE Sharp tomorrow in the syntax and editing session that is really about that topic as well. So we introduced in this paper a logic called RLTL modulo A. That is a combination of regular expressions with linear temporal logic, but modulo theories. And this whole sort of framework is based on symbolic derivatives. And for us, the motivating application is when we work with a project called Service Synergy, where we study properties of behavior of web services based on their Swagger specifications and learning sort of on top of that what they're supposed to do. So we're essentially learning a model of the behavior. So let me just give you a definition of what this RLTL is, and then I'll show examples of it and sort of motivated slides. So first of all, we have regular expressions. So predicates from a given theory A, which formally is defined as an effective Boolean algebra. You have the empty word regex, union, intersection, concatenation, clean star, and complement. Then we have a combination with linear temporal logic formulas that would be next, until, and release, plus the Boolean operators. And then we have the regular expression combination operators that talk, first two talk about the sup prefix of the input with the regular expression, and the formula phi is the suffix. This is why they're called suffix implications. And then I have closure formulas, weak closure, negative weak closure. And I want to draw attention to the two interesting ones are complement of regular expression and omega closure that are typically not supported by any other formalisms. We can also, so then there are also, of course, the shorthands for globally and finally as usual. And then I want to point out something that is very elegantly supported by derivatives. We don't talk about it in the paper, but I wanted to put it in the slide, which is, for example, adding new constructs, such as fusion. Fusion is a very interesting construct where it takes two languages and combines them by looking at the unifying element. So a word accepted by one regular expression R1 has to end with a letter that is then accepted by the regular expression R2. And this is commonly used in the context of PSL, so property specification language. And in the case of actually existential suffix implication and universal suffix implication, it also appears internally in the semantics. It's kind of an interesting sort of purely language theoretic notion that I haven't actually seen in regular expressions being used otherwise. So here are a few examples. Like in the pure LTL omega-Regularity fragment, you can say things like x is infinitely often positive, or x being positive is a stable property, it's finally globally positive, or things using extended regular expression, you can things like x is even in all even positions. That is sort of one of the classical examples by Wolper that is cannot be expressed in LTL. And then there's another interesting one, which is all proper prefixes of this infinite word match the regular expression R, which is kind of a combination of two negations. First, you have the regular expression complement, and then and that sort of transitions with the suffix implication to bottom, which is a kind of a complement as well. And this really illustrates the power of complement. And the reason it works is that you really never actually construct the automata when you complement, but you defer, you propagate complement along the derivative itself, and delay it, so you work lazily. So just to give an idea of where this can be used is symbolic model checking in RLTL, which can describe high level as follows. So you want to show that a given non-deterministic Buchi word automata, I will define it later, will satisfy condition phi in RLTL. You first apply the symbolic derivatives to construct an alternating Buchi word automaton. At that point, you apply alternation elimination to get a non-deterministic Buchi Word automaton, and this algorithm is described in the paper, and it's a generalization of Mayani-Hayashi 84 algorithms lifted to modular theories. And then finally, you build a product, or for a product, you also use a variant of this A algorithm. A is like Swedish pronunciation of the letter. And then here you can use classical algorithms. Beautifully, this 92 algorithm of nested depth first cycle detection is beautifully explained in the paper, and you can just essentially take it right there and put it in symbolic form, more or less as is. So some classical algorithms just work right out of the box. And of course, this whole thing can be incremental. All these steps can be joined into one because it's all actually lazily evolving automata, derivatives of formulas into automata. And I think the next 2 slides are going to be probably the most important slides of this talk to remember, which is sort of generic. So let us define what it means for a logic B to have a derivative function. So suppose that this logic is associated with a language semantics. So we talk about some words over some alphabet sigma, and we say that the set of words modeled by this formula is the language. Then we say that this logic has a derivative function when there exists for all formulas and all elements a mapping raw from phi and A to another formula such that the AW is in the language of phi and only W is in the language of the derivative of phi. So you saw already the definition of derivative from the last talk. I mean, the semantic definition. So this is the key here. So 2 examples. For finite words, you have the classical definition of Buzowski derivatives for extended regular expressions. And for this would be an example. So here, the D plus is just, one or more sequence of digits. So, and in the case of LTL, the rho would be precisely the LTL to the alternating Buchi automata translation given by Vardi in 95. Exactly. So there is really no difference. So, for example, if you take a formula such as globally x is always positive and remains even until divisible by 3, then of course this is now a formula in an infinite alphabet, which is quite typical in many applications, and you would typically do predicate abstraction and work pieces of it. But here you don't need to do that. You just work modular theory. So here, the alphabet itself is essentially interpretations of all the variables mapping to values in integers. So symbolic derivative of a logic now is essentially a partial evaluation of the concrete function with respect to a given formula. Again, note, for all elements, the term that is created is an if-then-else term, a nested if-then-else term, so that if you apply to the element, it evaluates to what the concrete derivative function would do. So for example, returning to the previous example, you would have 2 cases. Either the derivative, either it is a digit or it isn't a digit, in which case, if it isn't, you reject. Or you have a formula in LTL, in which case you will get 3 cases. I'm not going to go into details here, but you get, again, examples of how these leaves you would evaluate, follow the path according to what value x has. So transition terms have built up their own algebra. It's induced from A and B. So both A and B are sort of Boolean algebras, and the transition term is a new Boolean algebra that has its own rewrite rules that are really key. So when you operate operations in them, you often simplify them aggressively. So here would be an example where suppose you have this transition term, this nested if-then-else term that has some subterm in it, like a leaf or a subterm. Well, then you can apply the given Boolean law that applies to all Boolean algebras. You can simplify to F. We can essentially eliminate the disjunction. The same applies to G conjoined with the top element. Then now we can take the next phase, which is cleaning or simplifying this transition term even more by using the modulo A aspect of it, which here would be, for example, that if x and y are integers, then it is impossible that 0 is less than x, and y is greater or equal to, and x is less than y. So this branch is unsatisfiable, which means we can simplify the transition term to this one. But now the condition y greater or equal to becomes completely irrelevant, so we can just shortcut and eliminate it to this term. So that kind of illustrates a very common pattern that occurs in working with algorithms that work with these transition terms as a combined sort of combination of two algebras. So using this notion, we can now define alternating Buchi automata that I mentioned earlier as essentially 5 tuple that has finite number of states, initial state combination, and the mapping from states to transition terms whose leaves now are these Boolean combinations. And there is a final set of states. So here would be an example, and this would be the concrete representation as expressions, if and else expressions. Okay. We also mentioned a little bit about non-deterministic Buchi Word, which essentially are a variant of this where conjunction is disallowed. So your initial state is a disjunction, or the leaves are disjunctions as well, so don't allow conjunction. And we can sort of show examples of how sort of in the classical case, in the case of if we now take a fixed point of the derivatives, what kind of automata would we get? So here would be two examples, one in ERE, one in LTL. And here would be a kind of a picture that I showed earlier, but just connected to LTL here, it's a globally finally alpha and finally not alpha formula that results to this picture that you saw earlier. And if we now apply the algorithm here, you would get this 3-state Buchi automata, which really you can think of it as flattened form, as sort of a symbolic automata whose only accepting state is as 0 and that has an infinite acceptance condition. Now, let me show you one example of the existential suffix implication and how derivatives are combined. And this would be essentially symbolic derivative functions for RTL combined with those of ERE in a single framework. And for example, if you would take a formula AB repeated at least once as a prefix condition, followed by something that is globally gamma, then you would get something like this. And another example would be, phrase analysis, which I unfortunately don't have. And then time to go into. And the formalization in Lean, you can look in the artifact. And the thing I wanted to point out that the formalization in the math and Lean versions are really, really similar. So you can really follow what is in Lean as well as what is in the paper, I would say. And these are some future work items. Thank you.
Okay, do we have any questions from Margus? We have one right in front. Let's go there first. Please, in front. Keep your hand raised so I can see who the other questions are. Okay.
Thanks for the talk. In the middle of the talk, you presented the pipeline to go from RLTLA to Buchi automata via alternating Buchi, so you need Miyano-Hayashi for there. There has been a paper in 2015 about using partial derivatives to go straight from omega-regular expression to Buchi automata by non-determinizing on the fly. Yep. Do you think you could also do that and avoid having the Miyano-Hayashi in the middle?
Yes, I think that's possible, and it has to do with the normal forms of derivatives.
Yes.
So essentially, the mirror of normal form essentially is like a DNF normal form of the transition terms. Yes. If you work with those, you can often avoid the conjunction and directly get sort of a form that you're talking about. You're absolutely right.
Okay, good. Thanks a lot.
Yeah.
Oh, hi. Thank you. So I have a comment and a question. So first, I have been reading a lot of your and your collaborators' paper recently, and I really like them. I enjoy the vast amount of theory that you put out. But I realized one thing is that there's other part of other part of automata community which uses like bioalgebra technique, and I've seen a lot of overlap between you guys' work. It would be really nice to see how does this work connect. So that's the comment. And another thing is, so you mentioned like the cleaning part where you basically modulo the theory. And that, I think, recently I was trying to do that, and its structure is not too nice from a bioalgebra point of view. And so typically how people resolve that is to construct a automata directly without modular the theory. So every time you construct a transition, you modulo all the theory that you can modulo. Yeah, that's the question. Sorry. So have you considered that approach?
So I didn't quite understand the question here. So
Yeah. I'm not sure either algebras concept. Yeah, I'm not. Why don't we take that one?
maybe we check that offline because I'm not familiar with bialgebras, first of all.
Yes, I think we're gonna. I'm sorry. We're gonna have to cut off time for questions to keep on time. Please come see Margus after.